Okay, then hello, and welcome to my presentation, Exploiting Buffer Overflows on RISC-V. So maybe some words about me. I'm Christina Quast. I'm working as an embedded systems developer. I studied electrical engineering at TU Berlin, and now I'm living in France, in Nice. And in my university, I played IT security CTFs, and that's how I got interested in security. And that's what this talk will be about, partly. So that's what I will be covering. After the introduction, I will give you an architectural overview over the architecture, RISC-V. I will tell you what the differences to ARM and x86 are. And then we will directly dive into hands-on examples, how to exploit a buffer overflow, how to write your own shellcode for RISC-V, and how to perform read to libc. And I hope all those words will make more sense to you once this presentation is over. So what is RISC-V? RISC-V is an ISA, an instruction set architecture. It was started 2010 at the University of California in Berkeley, but since then it has seen many contributions. And since 2018 we have boards out there and hardware, because before it was just software written, a program which you could flash onto your FPGA to simulate a CPU. But yeah, nowadays you have hardware. And since March 2019, the version 2.2 is stable of this instruction set architecture, and you can start using it in your software development project. And to see how important this project actually is, you can see it by which companies joined the RISC-V Foundation, which are, for example, Google, NXP, NVIDIA, Qualcomm, Samsung. And so the advantage of RISC-V is that it's released under a permissive open source license, which means that anyone, you, me, and university can implement his own RISC-V architecture without needing to pay any royalties. So yeah, what is an ISA actually? Is whatever your CPU hardware understands. So it defines memory and registers, it defines logic ports which do the calculations between the registers. Yeah, it's basically like the machine language, which describes what your CPU is capable of carrying out. And so what your CPU actually understands is binary data. And that's what, but in order to make it easier for us programmers, there's the assembly mnemonic language, which we see here. For example, this one means add the immediate 559 to whatever is stored in the register A5 and store it back into A5. But what the CPU actually sees is just binary data, which means the same. And so why do we care that there is an open hardware implementation now? Why do we want to have an open hardware processor or CPU? Yeah, for one, it's the license fees I managed. Nowadays, for example, if you want to implement your own ARM architecture, you would need to pay royalty fees to ARM. Or so if, for example, a startup wants to make a quick prototype, or a university wants to use an architecture to teach it to the students, there was nothing on the market until now. So that's where RISC-V comes, for example, into play. And the whole idea behind RISC-V is also to democratize the process. So you have documentation to the chip, and anybody can join the RISC-V Foundation and discuss and find a consensus what kind of features to include in the architecture and which not. And anybody can join, which means be it a company or an individual. The project was designed to take all good ideas of architectures we have now in place and fix their shortcomings. So they want to be performant on microcontrollers, which usually are low on memory and have a low power consumption, as well on 64-bit processors. So how did I play around with the architecture? One possibility would have been to take one of the boards, but I thought it would be easier to just emulate it in QEMU. So I downloaded the image from the Fedora website and launched it, and ready I had a usable RISC-V system with tool chains where I had the libc, the a GDB, which I didn't need to try to cross-compile or anything. But the problem is it's quite resource hungry. So on my system, for example, it needs 3 minutes to start up. So it's not really optimized yet. But at least you have everything in place. You can just directly start hacking. So what is the RISC-V architecture? It's a reduced instruction set computer, which means you have small instructions which are not complex, which just do one task. Intel, for example, has push and pop operations to put things on a stack and take things from a stack. RISC-V doesn't have that. You need to address your stack relative to your memory. Your program counter cannot be directly written. Instead, you have to play around with the return stack, which is usually put on a stack, and you have to overwrite that. Furthermore, it's little endian, which means the least significant byte comes first and the most significant byte comes last in the memory. So if you want to write your exploit later, you need to kind of shift around the bytes, and we will see that later. So RISC-V has a modular approach, which means there's only one minimal instruction set which is obligatory to implement, and everything besides that is optional. The minimal instruction set has jumps, branches, logical operations, or add and subtract operations. But you can also add multiplications on integers, floating point operations, vector operations. You can add a 64-bit instruction set on top of that, and 128-bit instruction instruction set is in the works right now. And also you can use compressed instructions, which the compressed extension uses 2 bytes for one instruction instead of 4. So what else are the differences between architectures? So on RISC-V as well as on ARM, you would have, you can use your registers A0 to A7 to pass functions to parameters to a function. In x86 32-bit, it used to be that you have to put everything on the stack, but that's not true for the 64-bit version right now anymore. RISC and ARM have many more general purpose registers. They have 32 of them, while x86 64-bit has only 16. And the reason for that is on x86, most of the instructions have access to memory, so you can perform your add or sub directly on a memory address, whereas on ARM and RISC-V, you first need to load the value from memory into a register, then perform whatever operation you want to perform, and then put it back into memory. RISC-V is therefore called a load store architecture, while x86 is a register memory architecture. Then RISC-V instructions are, or memory access is byte aligned, while instruction access to instructions in memory is word aligned, which means every time you fetch an instruction, you always fetch 4 bytes, unless you're using the compressed instructions, which is only which support 2-byte instructions. And RISC-V got inspired by many successful CPUs which are already on the market, like Spark and PowerPC or MIPS or ARM. And all of them have a fixed width instruction set, while, for example, Intel is known to have variable size instructions which are harder to schedule or harder to fetch and decode in the CPU. And all those CPUs have a vast number of registers, so that you need less accesses to RAM, and accessing a register takes much less time than accessing a value in RAM, for example. And you have a very simple addressing mode. So this is the important registers we will be looking at later in our assembler code. For example, we have the 0 register, which is basically only 0. Which is useful in programming in general. For example, sometimes you want to compare whether a pointer is null or whether a value is 0, and you already have this register at hand. While in other architectures, you would need to clear this register first before you can use it for comparison. And furthermore, having the 0 register also reduces the instruction set, because you can use it for negation. So instead of having a negation instruction, you would just calculate x0, which is always 0, minus x1, which contains your value, and you have the new value. Then RA contains the return address. SP is the stack pointer. Then S0 is the frame pointer, which you will find later in the assembler code. And in A0 and A to A7, as I said, you pass the function arguments, and the return value of your function you can find after the execution of your function in A0 to A1. So I'm showing you the function pro and epilogue on RISC-V, because you will see this pattern basically later in the assembler code and might be easier to understand. So on the right side we see SD. SD stands for store double, which means it takes the value which is in RA and stores it at the memory address stack pointer plus 8. And LD is load double, which does the inverse. It stores whatever, or it loads whatever is located at stack pointer plus 8 into register RA. And so a typical prologue and epilogue is whatever happens or whatever the compiler puts without you knowing that. Like you write your little main function, and the compiler takes care of constructing and destructing the stack. Which means he basically makes space on the stack for 16 bytes, and then he stores the return address and the frame pointer from the previous function onto the stack. And whenever the function, like here's the normal function operation, and then you have the compiler has to or the code has to destruct the stack which he built up. So he stores back the return address and the frame pointer and destructs the stack. And jumps to this address which was stored before. So that's how it looks like on the buffer. As I said, this is your stack, and stack grows downwards, whereas address space grows upwards. So basically you have a lower address here, for example 0x00, and here the bigger address 0xFFFF. And so what happens if you have local variables? They are basically just stored after the safe frame pointer. So if you have a local variable and int a, which is 5, you store it here, int b is you store it afterwards on your stack. And maybe at this point you can, if you have a function like memcopy or string copy, it will still start from the lower address and will overwrite to the upper address. And I guess at this point you can imagine how a buffer overflow can overwrite your return address, which we will use later. So for me, hacking is like basically you're searching some blocks of Lego or Duplo, and you build up your tower to create an exploit, and that's what we are going to do. We are going to search for stones to build up our tower. Let's start with a buffer overflow. So for example, we have this function, which is vulnerable to buffer overflow, because you have a buffer of 8 bytes, and you're not checking the size of the buffer, you're just overwriting with whatever was passed to a function in argv. And then let's assume you have this magic function, give shell, which just opens a shell for you, and you can do whatever operation you want to do afterwards. So what we want to do is use a buffer overflow to overwrite the return address of the usual function with our give shell function, which gives us all the writes. And so basically after the buffer overflow, we don't care what is in the buffer. We want to put any valid address into the safe frame pointer, or it depends, sometimes you don't care. And we just want to be sure that in this address on the stack, we have the give shell address later. So how do we go about? How do we approach this problem? So first of all, we have to find the address of grep shell, and we can use object dump minus decode for that. So we have our address, and then we just play around with GDB. So we pass some input into our program and see where it crashes. So in our case, it crashes at this address. And for those who have played around with hex a lot, that is basically hex byte 0x41 is basically just A in hex. And you wonder why this one is a 40 instead of a 41. As I said, RISC-V access to instructions is always at least 2 byte aligned or half word aligned. So that's why you can never have a 1 here. So next step would just be to replace whatever is here, all those A's, with the address we found before. And that's what we do. And as I said, RISC-V is a little endian architecture, which means you have to put the least significant byte, in our case 0xC0, first, and then the rest of the bytes. And you see that shell is spawned, and you can just do cat etc passvg, for example, at this point. Yeah, and then you just have to double check that it works on your local system as well, outside of GDB. So, but what do we do if we don't have this magical give shell function? What do we do to get a shell in this case? In that case, you can write shellcode. What is shellcode? Shellcode is some hex bytes you can pass to the CPU, which will spawn a shell for you. It will basically do the equivalent of system with the string bin_sh in it or something. And normally for known architectures, you can download most of your shellcode from Shellstorm, a website. But since RISC-V is a new architecture, we have to do it by hand this time. So yeah, so this is the basic idea. You find some executable area in your memory, like the stack or the heap. Sometimes you have to leak the address, but in our example, to make it easy, the program will just give us the address. And then you write some assembler code, put your shellcode into your buffer, overwrite the return address, and jump there directly. So that's our vulnerable function in this case. Again, we have a buffer, which in this case is 128 byte big, and that's approximately the space we have to put our shellcode. It can be up to 128 byte in size. And again, we have a string copy, which does not check for any size of your buffer and just overwrites whatever it finds. And again, we call it with the argv1 argument, so whatever is passed to your program. And so how do we go about? We can, for example, start and take execve, and execve will execute any program you pass as the first argument as a string. And we will pass here the string bin_sh, and about those arguments we basically don't care. So first we have to find out, so execve is a syscall, so we have to find out the syscall number. And for that we can either look into the header and see, okay, that's syscall number 221. Or we can again look at libc and see how this function is called. And libc will just load the number 221 into the register A7, which is designated as the syscall number register, and then call the instruction ecall. So so that's what we basically want to do. We want to pass bin_sh to execve, and the other arguments we don't care, just null. So then my idea was to make life easier, I will not start from scratch writing assembler code. Instead, I will just implement a C function, compile it, and see what it does already. So this is my C function, and this is the resulting shellcode. And as you can see, that's basically the prologue and well, we don't have an epilogue in this case because we don't care what happens with the stack afterwards, but we see the prologue we saw in the beginning. But the problem now is Yeah, but in that compiled function is using the PLT, the procedural linkage table, which is a mechanism where a program can find dynamically where libc functions are located. So basically it's like a trampoline. It goes to a place, searches for the address of the real execv and jumps there later. And yeah, so instead of going around circles, we can just directly put whatever the execv function does in there and have our resulting shellcode. Yeah, then you compile it and you execute it and you double check that it works. But at this point you have a problem because you have null bytes. And you know what happens with string copy if you pass something which has null bytes? It stops copying, exactly. So you don't want to have any null bytes in your shellcode because you will not copy the whole shellcode then. So after having this base of a shellcode, you want to remove all the null bytes. And how can you do that? Yeah, for example, in the original version, it used a power of 2 number in order to adjust the stack. You can use an odd number, let's say, in the base 2 system in order to have a function which doesn't use null bytes. And then you later have to adjust the offsets when you are referencing S0 as well. But then here, for example, we are loading the immediate value 0x687 into our register A5. And instead of doing that, we can take a larger number to remove null bytes. And then we have to account for the offset we created by doing more operations, which makes our shellcode bigger, but at least we removed the null bytes. And then the last problem we have is the echo instruction. And we have to perform it as is. So in order to remove that, in our case, we are lucky because we have a writable stack as well. So basically, with this shellcode, we are creating exactly this combination of numbers and putting it on the stack, and then we are jumping there. But it only works if your stack is writable. So what we see here is exactly the shellcode we just created. And that's exactly what we want to pass into our buffer. Yeah, so you find it here again, same shellcode. And so we overwrite the buffer with the shellcode, and then the rest of the buffer size we fill up with 8 because we don't care. This is where the frame pointer would be located, and this is the address we want to jump to. Because luckily our main program just gave us the address where the buffer is located, where our shellcode starts, so we can just jump there, and we are greeted from our shell here. And so, but what happens if our stack or heap is not executable? Because that's what a program normally is, right? You don't want anybody to execute code on your stack. Then you can perform read to libc, which is a technique of ROP, or return-oriented programming. So yeah, let's assume that's our vulnerable program, and it just reads in whatever it finds in the file we pass over fd. And yeah, that's it. And our stack is not executable. We can try to perform ROP now, and ROP means you basically search, you know what libc version is running on your system, so you know what possible assembler instructions you have in this libc, and you're searching for assembler instructions which do something, and then do read. In the best case, it loads a value from the stack in the registers you need, and then it does a return. And you basically chain those so-called ROP gadgets one after another, so that you have the execution of the program you want to execute. So for example, in our case, we want to execute the function system, which again, we pass the string bin is age. So yeah, first we have to find our ROP gadget. Again, we use object dump -decode for that. We grab around, and out of the 1,000 gadgets, I found this one is nice, because what we want to have after our buffer overflow is having the address of system in our register RA, the return address register. We want to have the address of the string bin_h in A0, which happens here, and the other two we basically don't care. And we want to overwrite our return address on the stack with that one plus the offset wherever libc is mapped. So next step is we have to find out where the address of system is actually. We use object dump for that again. And bam, there's the Python script which will generate the file with the exploit in it. So we fill the buffer with A's because we don't care. This is the frame pointer again. And this is the gadget address we found. So the shellcode I showed you, which basically initializes the return address and A0 for us. And then on the stack further you find the address of this string, bin_h. Yeah, obviously you need to have address space layout randomization disabled at this point, because otherwise your address will change all the time. Then, yeah, the address of system in the buffer. And so this is the generated, that's the file called exploit generated by Python code, which is read in our program into the buffer. So we see this is the A's, for example, the B's, and the addresses, yeah, in the code as well. So we just pass it to our function vuln, and it opens a shell for us. And actually, I used, like normally, if you want to try out your exploit, in this case, in GDB, the problem is that GDB puts environment variables into your stack. Like, environment variables are located on the stack, so it will move around where your buffer is located in the end. So in order to facilitate that, you can either remove it by hand, or you use this fancy script called fixenv, which you can get from GitHub, and it will adjust your stack for you. Yeah. That's basically it. If you have any questions, feel free, but otherwise I'm giving away some RISC-V boards and hardware. If you have some fancy project, come talk to me and I will hand you a board and maybe tweet about what you want to do to motivate you more. Yeah, that's all. Do you have any questions? Okay.
You said earlier that we have 32 general purpose registers, but only 0 to 7 is used for argument passing.
Yeah. The rest you pass on the stack.
Should I repeat the question? Hello? The problem with going first. Hello? Okay. You said earlier that we have 32 general purpose registers, but only 0 to 7 is used to pass arguments and return values. So I was wondering what happened with the rest of them.
Yeah, the other is, for example, the null register, or the return address register, or frame pointer. Yeah, so basically they are used, but they are not used from argument passing. Or temporary registers, where you just store values, but you don't, they are not defined as passing to functions registers. Yeah. There was another question, I think. No?
Hello, wait. I have some questions because the shell point, or we say the function you called when you return, that is the code you can access in your Linux OS.
But which page is it? Do you know?
I think everyone like some shell you can return and create a shell command console. Maybe.
You say stop?
Yeah. Okay.
Yep.
Yes, after you run this program, you will just run the vulnerable function.
Yeah.
And this function is the code you can access, or the memory you can access, or because OS or Linux have some memory MMU.
Yeah.
That will limit you access the page you want to.
But you put it on a stack. So basically, you can access buff, right? So you can also access buff plus 12 or buff plus 42.
Okay, that page you can access. You have the authority to access that page.
All the reads and writes and executions I did, you have the authority to write at least. And in this example to execute as well.
Okay, because if you are in kernel space, that you can access it.
But this one is not in kernel space. This one is, for example,
user space.
But I mean, the same techniques apply in kernel space. You're just accessing what you can use in your program as well. You're in your thread. Mm-hmm. You're not looking at thread 2 or 3, which does something different. You're in your address space, basically.
Also, if I have one function in my main application, and another one, another users write their application.
Then you don't.
So I cannot.
You can. It would be much more complicated.
Okay.
This one basically targets one program.
One program that I can access the full memory.
The easy examples. Yeah.
Oh, okay.
It's not the complicated examples where you have to access other users' space.
Hello, I have a question about that. About our ROP attack. I think that you have a fixed event, fixed environment to the shell script. Mm-hmm. So I think that may be the ASLR disabled.
Yeah, for all those examples, basically ASLR is disabled because, I mean, otherwise you have to run it 1,000 times and it might do the same.
Yeah. And what is the effort for you to find that gadget?
For normal architectures, you have actually programs. Like for ARM or x86, you can call robgadget, or there are Python modules which find.
Okay, you have a tool, right? To do.
But yeah, since that one is not, it will be implemented, I think, in the next month. But but for now, I just use grep.
Okay. And have you compiled the same application that compiled for both by on the RISC-V and that on ARM? Any code size change?
Any?
I mean the code size change difference compared with.
That's in any case, you have different architecture, you have different instructions, you have different code size.
Yeah, I mean, which one is a smaller?
Depends. I mean, my shellcode is not very sophisticatedly written, so you can make it smaller. I think you can just put it in 32 byte or something. Depends on how much time you want to dedicate to write your shellcode. But actually, RISC-V and ARM are quite similar in terms of instruction set, in terms of philosophy. Most techniques you can apply on ARM, you can also apply on RISC-V nowadays.
Okay. And so actually you...
And also, like if you're asking about normal programs, it depends highly on your compiler, how well he can optimize for the platform.
Yeah, you mean for GCC they have optimized on the...
yeah, I don't know how good their optimization for RISC-V is.
Okay.
For example.
And can you go back to the general register compiled the slides, which is the difference in the arc?
Yeah. There.
Yeah.
That or the previous?
The next one. Yeah. Was everything compiled with ARM that like the banked register is same in the RISC-V design?
Say again?
I mean the banked register.
Banked.
yeah, when you switch the context and
Yeah.
I mean the privileged mode, the same bank, some register will be banked.
I didn't look into that,
Okay.
but I guess it depends on your implementation.
Okay. And yeah, I can change to the next question. That you have mentioned that there are compressed instructions.
Yeah.
Compared with the sum mode. So this is be dynamically changed. Like in ARM we have a BLX, but in RISC-V
It's implicit.
it's
Yeah, it can directly decode. You don't need to change between modes. Like you saw in the shellcode, for example, I presented somewhere. That you have instructions which are 2 byte in size and instructions which are 4 byte in size, and you don't need an instruction in between. It just works like that.
okay. So
It's implicit.
okay, thank you.
Yeah. Thank you. Time's up. Thanks a lot for listening. And if you have more questions, come and talk to me. I'm happy to talk about those topics.